Our final speaker is Elizabeth Stockdale. According to some words she scribbled here, Newcastle University, North East of UK, but not a Geordie. Play with soil and teach other people too. Elizabeth.
I'm from the UK. I'm travelling just for a short hit into UWA and then across to see you guys on this trip, but I've been involved with the soilquality.org.au project for a long time. I get to come and referee, basically. So we have had a number of workshops where we've got farmers and advisors together to work out how to present information, how to put it together. And unsurprisingly, around those tables, there's always a lot of vested interest. So my job around those tables is to act as a referee, as an independent, impartial person, to say, come on, guys, can we make it work or can't we? We've also got an interest, of course, in taking that kind of information to the UK, but I've not managed to sell the kind of opportunity you guys have through that to any of our funding bodies yet, but I'm working on them. I've been asked to talk today about increasing soil resilience to environmental risk, and I'll try and do my best. You'll see that my slides are kind of there just to stop me kind of going off on every tangent known to man. Because give me a topic about soil, and I can talk about soil, about how to manage it, how to use it, react to your questions, think about them, start having a conversation with you for possibly 2 or 3 hours, and you don't want to be here that long. So I've got my slides here to really try and keep me on track and get us to finish at least approximately on time. This one's here to remind me to say something that's incredibly important, which is that there is no such thing as soil. Every soil is unique. It belongs to its place and its management. It's a result of the interaction of the geology that underpins the piece of ground that you're on, and that can be actually very shifting geology, such as in a river catchment where sediments are changing year to year, but it can also be incredibly stable geology. And it's really interesting for me as a sad soils geek to come to Australia and see sites that have had opportunity for soil formation over a really long time, because the UK doesn't have that. Our recent glacial history means that we have very young soils that are very different. But that interaction of geology and climate over time with the vegetation that comes into climax with that, then interacting over the last 100, 150 years of management creates a unique equilibrium situation in that particular location. And when I say that particular location, it might be that there are 2 or 3 of those kinds of equilibria happening inside every one of your paddocks. It might be that you're lucky and have paddocks that literally are the same 2 or 3 next to each other because they've had the same management and the same conditions. But it's actually much more likely, even in your landscapes, that you've got variability because of depth, because of differences in geology, because of differences in management. And we've seen some patterns like that put in front of us on the GPS. So what's not important is that you understand the details of the science. What is important, though, is that you are able to bring together your practical understanding of your soils in your place that you've been managing, together with some general principles of the science, so that you can then do something to improve your environmental resilience, to keep your production going forward. So if we want to think about managing soil quality, what we're talking about is actually creating an opportunity for the soil community that Dan's already talked about to actually deliver a whole range of things. Because even in a farm situation such as you have in Australia, where the focus is really away to the left of this diagram on the need to produce food and fibre from soils, actually soils still need to deliver, still do deliver, whatever we're doing, a whole range of other functions too. Because the way that water moves through soil is critically important for the recharge of aquifers, the movement of water into rivers. And the things that are happening on land, drainage, how structural stability is measured and monitored, whether there's soil cover, and so on, have a huge impact in that water regulation through the system. And it's why it's really exciting for me to see management at catchment scale. It's just about beginning in the UK too. Of course, soils are a really easy system to understand. Yeah, often we show this kind of diagram going, oh, as a nice sort of 3 or 4 overlapping circles thing where we go, oh, it's really easy, there's just physics and chemistry and biology. But of course, within each of those, if we talk about physics, we're talking about compaction and bulk density and aeration and water balance and pore size distribution and temperature and texture and how that interacts with buffering capacity and CEC, which is getting us into chemistry, but overlaps with the physics. And hey, we can drive ourselves mad really fast, and I'm a scientist. I'm supposed to understand all this stuff. So if we want to understand how the soil functions, often we have to stand back and look at the big scale. We have to look at the function. Is the plant getting what it needs when it needs it? And hey, what better to ask than the plant? So tissue testing, and I get shot for this on many platforms when I'm a soil scientist, but tissue testing is a really useful way of asking the soil if the plant's getting what it needs. End of yield sampling for things like grain protein are a fantastic way of asking the plant if the soil's managed to deliver things over time in the way that's needed. If it hasn't, the way to fix it might be complicated and might involve playing with a number of these things. But in terms of regular long-term monitoring, we need to find things that are easy and quick to just tell us if we're on the right track. Because most of the time, that's what we want to know. Not the detail, but the general principle. Have I actually managed to get the management just about right in the conditions that I'm working in? Given that my soil, delivering this function, sits within a particular climate and within my particular management system, those 2 arrows coming in at the top. I'm hoping that you can't see the numbers on the jar because they're not as amazing if you can see them. But one of the things that I think always and continues to astound me is that soils, however degraded they look, are incredibly diverse in terms of their biology. And you all luckily missed it, but I was on the radio earlier today and was talking about actually the diversity of the life below ground being greater than the diversity we see in the Amazon rainforest above ground. So we look at that and talk about that as being such a biodiverse hotspot and how important it is to protect and all these things. And actually our soils beneath our feet, where we don't look and don't see this very often, are more diverse than that. And I think the thing that strikes me most, that's a UK pasture soil. It's not that different in terms of its numbers than the kind of pasture soils across here. Though if I show this slide in WA, they kind of don't recognise that as soil. It's completely the wrong colour. But we're talking about the fact that there are individual bacteria there, and the number has 12 noughts on it. So inside a jar of that size, we're not short of individual bacteria. I think the thing that always surprises me is that there is 10 kilometres, yes, 10 kilometres, of fungal hyphae within that jar as sampled. How can that fit in there? It blows my mind every time I use that number. It just doesn't seem to make sense. But of course, what we're talking about is a completely different scale of world. So the world beneath our feet is kind of at the same scale remove as we are to people looking at the Earth from space. And actually, that's not a bad analogy. The picture Dan talked about a very small proportion of the soil surface being occupied by these bacterial communities. If we think about pictures of the Earth from space at night with the clusters of, we could probably identify Albury Wodonga, we could see Sydney and Melbourne, but probably not huge amounts of things sometimes in between. It's the same sort of picture if we use fluorescence to take pictures of the soil. But this biology matters, and I know you guys know this because I know you've been bullied by Suzanne and others to think about this sort of thing. But it matters in a way that wasn't ever taught to me. It's something I've come across and been immersed in subsequent to my training as a soil scientist. We used to think that physics and chemistry were mostly all we needed to know about soil unless we were producing antibiotics. But actually, if we want to think about the kind of processes that we need to manage and make work for us, they emerge from the interaction of the physics and the chemistry, the habitats on that diagram, with the populations that live there. And the processes emerge out of the middle. And it's that interaction, that dynamic world under our feet that is ours to control, or at least to work alongside. So we have the opportunities for us set in the way that Dan was talking about, that a number of site factors through influencing populations directly and influencing the structure of the soil, the space and the surface areas, and the interaction with air and water, climate, soil type, topography, set the baseline against which our management, the things we are able to do, interact with that system. And the things that we do interact, of course, both directly and indirectly. So even something that seems as obvious as an impact on a soil process as applying a bit of nitrogen, that's surely just improving nitrogen supply, isn't it? Is also going to cause plants to grow better. It may improve rooting. It will certainly increase the amount of carbon going through the roots into root exudation. So it's going to feed the organisms in the soil in a different way. The timing of that application might be critical, whether I've done it with urea or nitrate, with a liquid or a solid, that's going to matter, and it's going to interact with what's going on. So even something as simple as applying nitrogen fertilizer could end up having a huge mixed bag of effects, which is why scientists like me aren't very good at answering your questions that you'll ask me at the end, like, what'll happen if I do this? And my answer is always going to be, well, it depends. But the important thing is we get ourselves together to a place where we understand what it depends on. Because if you understand how the response depends on the things you do and the situation you're within, you can manage that more effectively if things change. We know that if we're thinking about environmental risk, what we're really talking about is weather patterns. We've just seen a fantastic example of how, let's not worry why or how, that weather patterns seem to be changing. The pattern, the seasonality, whether we're getting huge amounts of rain when we didn't expect them before, or less rain in this season than we expected before. Things don't seem to be stable at the moment. So being able to understand and respond and build in capacity for that complex system within our soils to respond to those changes is going to be really important. And those aren't changes that only matter because they affect water. They're affecting a whole range of other things too, and the biggest example in your local area is probably the impacts on salinity and sodicity. So if we change the water balance in a site, we're going to potentially change a whole range of other things that start to drive chemistry as well as the physics of the system. So we just go back to a dull bit of science and look at resistance and resilience to stress. It doesn't mean anything very clever, because we just say, here's a response variable up the left-hand side of that graph, i.e. we're measuring something. And actually probably the most obvious thing we might measure is yield. So in general, we expect a particular level of yield, in this case probably in response to a particular level of rainfall, and we know how that works. We know French and Schultz. Even I, we don't do water efficiency in the same way as you guys, have been to Australia nearly for long enough to be able to quote it, but not as well as Murray did on the radio this morning. So we can look at the resistance and the resilience of our system to change. And those two things often are mixed together when we go on and talk about resilience, but they are strictly separate things, because resistance, well, we know what that is. If I push you, how far do you fall over? Yeah, do you manage to keep your footing, or do you fall all the way over? And of course it's going to depend on how well you were standing before I pushed you, isn't it? If I sneak up behind you without you looking and make sure I do it when you're only standing on one leg, hey, I can really make an impact. But if I make sure you're actually fairly well grounded, yeah, feet well apart, shoulders, all that kind of thing, you know about football better than me, and I give you a bit of a shove, you're not going to go anywhere. You've got very little change to the disturbance that's been put upon you, yeah? Resilience, well, that's how long it takes you to get up and punch me, isn't it? Yeah? The time it's taking you after that disturbance to regain your balance and get back to where you were before, and then potentially go on and react. Yeah? So the degree of change, if we see a stress, and then the amount of time it takes that system to recover back to equilibrium. It may be, of course, that if the stress is a one-off, we can go back to the equilibrium we started with. It may be that what we see, and actually we may be seeing with climate, is not a one-off stress that's changed once and is never going to come back, but is a gradual change process where we're needing to establish a new way of working, a new equilibrium for us and our soils in this new world of management. The kind of one-off stress we might see is a flooding event, a 1 in 200 year flooding event or something like that, that we don't need to think about. This might become a recurrent and regular thing. In 2002, John Duran in the States identified 4 really key integrating things that needed to be done at farming systems level. And soil scientists, he is one though, so got quite excited. And because he managed to mention soil twice, which is good for us. But I think if we'd got a plant scientist to write the changes that needed to be done in farming systems, maybe there'd have been more plant ones in there. But we have here a need to look at a whole system. If we want to increase sustainability, which is, I guess, the same jargon, isn't it, about increasing resistance, improving resilience, i.e. we manage to keep things on an even keel much better as we run into the future. We're looking at not just being one-faced as we look at our production system. We need to think of it in its holistic context. That isn't, and it's a much bigger driver for farmers in the UK, but it doesn't mean that we can disregard the balance and the interaction with water demands in the environment around us. It doesn't mean we shouldn't actually be already starting to think about, are the resources that we're bringing in from outside the system actually renewable and fit for purpose in this system as it rolls forward? That's just as important, actually, as the management on our farm. Because implementing a new management system, and I think they're great, such as precision agriculture, presupposes that the electricity to run all of those kind of systems is going to be there as we roll forward. I think we're safe for 50 to 150 years with that one, but we should actually kind of have some of those things in our minds, and we do. The cost of diesel is enough in the UK for farmers to be downsizing tractors. Shock, I know, but nonetheless, the cost and fuel efficiency considerations are enough to mean that farmers are thinking through that in a way that, in my lifetime, they never did. So if we just look at a soil plot in relation to resilience, and the science can get really complicated, so here's a diagram that I'm not going to explain properly, but it's got some stuff on there if you want to ask me later, go, oh, hang on. So this is a diagram that compares stubble burnt, unfilled in circles on the right-hand side of the graph, and stubble retained, filled in circles on the left-hand side of the graph. Data's from long-term or longish term trial in WA at Meriden, in a cropping system, comparing those two treatments. I suspect, and I'm just trying to look at him, that it's some of the data that Dan showed before came from that trial as well. So what we're looking here is actually the soil response. So here we're not measuring yield, we're looking specifically at soil resilience. How does the properties of the soil change through the growing season when we put this external stress onto the system? And we can see actually that the same sort of seasonal pattern, one of those sort of wiggly things, happens as we move from May to July to September to November. In both the stubble retained and the stubble burnt, we get the same sort of squiggly diagram. The seasonal pattern is similar in both of those systems. But they're different from one another. They're stretched apart on this graph because of some things that we've measured that show those differences. And the most important thing for resilience is that the stubble burnt system has a much more stretched out response than the stubble retained system. So it's just as showing you that it is possible to measure resilience. Retaining stubble in this system, in this particular trial, in this particular location. Let's not make great claims for this. I'm a scientist. I never actually make great claims for anything. I always hedge my bets. In this system, we've got increased resilience in this particular set of soil properties we've measured because we've retained stubble in the system as opposed to burned it. So we can measure it and start to understand how resilience of some soil functions, the ones we can measure easily, are affected by management. To give you an example that probably is entirely irrelevant, but hey, this is a typical mixed farming system, probably a dairy, sort of not the very close fields to the dairy farm, but the kind of next fields out where the grass clover lay would be cut for silage in the middle of the UK. So we're talking about 600 to 750, 600 to 900 maybe, though it's unlikely to be quite that high rainfall, in the UK. So sowing winter wheat, following the grass clover lay, possibly sowing an overwinter cover crop, coming out into spring barley, because we grow quite a lot of spring barley because it's got a good market for malting, into winter beans, into a cover crop. There's a reason you will see any minute now why I've chosen this rotation. It's because I want you to be able to see the conventional versus organic comparison. A standard conventional producer in the UK wouldn't be growing this rotation. It's much more common to have wheat, barley, often winter barley, but sometimes spring, canola, we call it oilseed rape, back into the grass clover lay if you're that point in the rotation. So if we're going to look at the impacts and the resilience of this farming system, the soil within this farming system, we have to understand the system and actually the management and what's going on before we can start worrying about its resilience. So this is what's going on. Yeah? We've got livestock. In this case, I'm suggesting this is beef, cattle and sheep, which have some permanent pasture, but this lay's cut for silage and they go on there for some limited aftermath grazing. We've got careful variety choice in an organic system like this. And if we contrast that with what would happen in the conventional system, of course, the difference in terms of crop protection, weed management is the use of pesticides. Actually, the conventional comparison system wouldn't use cover cropping very often, would tend to go in with a winter rather than a spring cereal. Obviously, the difference in terms of rotations and so on. But keeping that system as the heart, what are the implications of just the change in system? Let's not worry about poking it and trying to make it fall over, first of all. Let's just look at what the difference is. So there's the system. If we look at yields and productivity, under that suite of organic practices, which are practiced as a suite because they give you a little bit of an edge in the market in terms of marketing, whereas if you go with an IPM approach, you might adopt most of the same practices but not get any extra money. So we're talking about crop yields on that system in the UK, 70 to 90%. So a drop in yield, but actually often, but not always, offset by the premium. Lower stocking rates, but the same productivity per unit livestock. You've heard from Dan about the differences in organic matter, so the important thing here is that in general you do see increased totals and active organic matter, but you don't see it if the conventional system has the similar sort of pasture in it. You do see it if you're comparing it with a really traditional mixed system that would be 6 years of cropping, but often not because of the pasture inclusion. You definitely, though, in those systems, even in a system that includes pasture in a conventional system, will see improved ag stability, hence lower diesel costs for tillage. Small differences on average across the rotation in biomass, but if you want to be clever, you go and look at the particular bits of the rotation, and there's a huge difference in biomass through that rotation. What about the bigger picture in terms of ecology? Well, we've got actually really good evidence that there are increased populations of a whole range of larger organisms that are dominantly Collembola mites and other large organisms driven by the increase in biomass, or the increased turnover of biomass at least. So one of the reasons that we don't have a big change in microbial biomass between these systems is if you increase the food source, hey, what do? You increase the predators. So you might have more more Collembola and mites because there was more microbial biomass. That means there's less microbial biomass now held in check. Earthworm population, they're dull. Don't get excited about earthworms. They're dull. They're vegetarians. They wear sandals. They don't get involved in the hurly-burly, eating one another world below ground. Yeah, they kind of hang out separately. The thing that drives the earthworm population in soils is the amount of particular organic matter going back into those soils on a regular basis. If you have small, regular inputs of organic matter into systems, you will maintain a healthy earthworm population. And if you don't drive through them every so often and chop them up with your plough. Biodiversity, we would get most above ground taxa increase in organic systems, similar on-farm energy use, but lower indirect energy use. So this is the kind of energy use we measure if we start counting how much energy is used to produce nitrogen fertilizer, for example. Okay, so the point of showing you that was I'm now going to poke both of those systems very hard and try and make them fall over. Yeah, I'm going to apply to those systems my understanding of what's happening with climate change for the UK where these systems are based. So we are expecting in the UK warmer and wetter winters, warmer and drier summers. Oh, please let us have a dry summer this year. But that's what, on average, we're supposed to get going forward. Similar total annual rainfall, but we've got a greater seasonality in that. So we've got actually a stretching, a pattern that will take us to be more Mediterranean in terms of our rainfall. So we will actually start talking about summer droughts in a way that we definitely don't, based on last year. So we're going to poke this system and see what happens. Okay, so actually in the UK, we're happy because the modelling suggests, are going to get better yields. It'll be marvellous. Yeah, we're actually expecting crop yields to increase overall and actually for the cropping pattern to spread north in the UK, so we'll have a greater range of crops available in my bit of the UK than we currently have. Maize hasn't made it as far north really as me yet. It's coming, so it wasn't within 200 miles 15 years ago, it's within 50 miles now, it's coming. That summer temperature that we need to grow maize is allowing that to come in as a break crop and as a dairy fodder feed, not dominantly to produce seed just yet. So there will be issues for the south of England. The south of England is going to become more like Spain, i.e. more Mediterranean, really have droughty summers. But in general across the UK, in either of these systems, whether conventional or organic, what we're going to get is bigger yields as a result of climate change. So consequently, if I'm going to directly adapt my rotation, I'm not going to have to do very much. Yeah? I'm going to have to do some things. I'm going to have to be a bit awake because I might have to change my varieties. I might, if I live where I live, in the North East, look south for the best varieties. But I'm probably not going to have to change my cropping significantly, but I might use different winter wheats. The guys in the south of England might start looking to France for their germplasm and their breeding stock. I certainly might change sowing dates and think about sowing dates and harvesting patterns in a different way. So I might be looking for earlier, in the south of England, certainly earlier maturing wheats and so on. So there'll be an issue with getting my flexibility of my system right, but I'm not going to have to make any major changes. I think the bigger issue for the UK, and I'm only modelling this so as we talk it through, and you kind of go, okay, I can think about how it might work if we talk it through for our systems, because I'm not brave enough to try and do it for you, is that indirect impacts in the UK will have a bigger effect. So if we really think about this kind of climate change, the scenario rolling forward, what we're probably going to find is that alongside the change in climate, we've also got a constraint, or at least a higher cost, of fossil fuel-based resources. We already see that. Fuel costs are going up. Consequently, given that natural gas is a base product requirement for nitrogen fertilizer, let alone its energy demand, let alone the energy demands that are encapsulated in pesticides, there's going to be an issue in terms of those fossil fuel-based resources. And we've heard already that although the window for phosphorus use is stretched out, it's still there as a limiting factor, and thinking about using it more effectively might be a good thing. So all our current management systems, as they're currently set up, are on a bit of a wobbly base here because of their dependence on those things. So what about organic farming in this context? Well, actually, as you roll the model forward, you actually lose really any difference. The systems become much more similar. Because the organic system's increasing yield, the reducing fossil fuel means a marrying, actually more shared learning, which is great, between the two sorts of farming systems, and we're already starting to see it happen. But the big driver in the UK and lots of other places will be about needing to reduce on-farm fuel use. And actually, it's one of the reasons that the UK has finally woken up to the concept of conservation agriculture and no-till. We're not in a dry land situation where it's driven by a need for water conservation, but the need now to save money on diesel is really getting people to think about it and think about it in a different way. So if I was going to make recommendations in the light of climate change, the general principle information is not any different from the UK than it will be for you. Because if we want soils and soil systems to be in a really good place before they get poked, we need them to be as healthy as they possibly can be all the time. If we think about that system that's driven by the microbial biomass interacting with its geology and climate in its locality, what do we need? Well, we need it to be healthy. What do we need to be healthy? Well, we need a good place to live and something to eat. And then once we've got that, we can start worrying about exercise and so on. It's the same for those soil organisms, that interacting set of processes that happen below ground. We need to remove the constraints. We need to look at and identify what our constraints are. We need to promote soil organic matter, and we're doing that, not because we're interested in carbon farming, but it'd be marvellous. You guys are well ahead of us on that. It'd be marvellous if you could get paid for doing things that did that, but do it anyway, whether you get paid or not, because you'll put your soils in a much better situation by minimising tillage, in reducing the disturbance where you can to the soil. It doesn't necessarily, because for many weed management systems you can't go to zero, but you can always think about, can you do less? Increasing the inputs of organic matter, and particularly important, increasing diversity in the system, varying crops, not just in time by rotation, but in space. If I've got that precision map, do I have to crop everything the same? If I understand how my current systems are affected by current extremes, whether in weather or in something else, I'm actually going to be in a better situation if that variability increases. I'm going to be able to increase the adaptability of my management within the constraints of my markets. The important thing is about knowing my soil, not me knowing your soil. Hey, it doesn't matter if I know your soil or not. You need to know your soil, yeah? You need to know it. You need to have the information at your fingertips that you need, and you don't have to have it on an iPad. If you really want to, pencil and paper does work for doing these sorts of things. iPads do take us another step forward. They make things more accessible, but I'm old-fashioned. I don't have one yet. I'm still, when I'm thinking things through, a pencil and paper, drawing pictures, thinking things. You can do soil management that sort of way too. It might take you a little bit longer, but the important thing is that you understand your soil. And I mean the soil on the left, not the bag of dry stuff that isn't really soil anymore on the right that you've sent off for analysis. So if you do send off soils for analysis, know where those soils came from. We've heard that as a message in relation to phosphorus. Understand where your samples come from, how they fit in the system, how you're planning to use the information and take it forward. We can do clever stuff now and map our variation across paddocks and start to put those pictures together to give us an enhanced detail of our information. But precision farming isn't only about space, it's also about time, and if nothing else, it's mostly about information. One of the reasons I got involved with this website is that it gives you guys access to information that you can use to not to see general patterns, though you can do that if you really want to, but actually to benchmark your practice on your farm through time. Accessing the kind of information that's useful. Not everything has a traffic light, because not everything can have a traffic light. And we worked very carefully. I was at a meeting where a lot of shouting went on about whether it was possible to have traffic lights for phosphorus. And the answer is no, it's not. Because phosphorus management, nitrogen management, is a farm by farm, field by field, minute by minute for nitrogen decision, not one that you can do by looking at information on a website. But there are some things that it is useful to know, how do I fit into the benchmarks? If there's this spread in phosphorus numbers in my region, where do I fit? And why on earth is there that spread? What's causing it? What are the factors that are driving it and causing the difference? I'm not going to answer any questions because, hey, my understanding at farming system scale of the impacts on soil quality is very sketchy, especially in your climate. But I would give it a go. But there is increasing evidence that if we want to improve resilience of systems, we need to think about farming systems, the whole farm, interacting together, not paddock by paddock, but we need to think about how the biological activity is the driver and we can work with those things together. In the UK, potatoes are the worst thing you can do to soil. I'm sure you have a similar crop that just absolutely annihilates everything known to man and turns the soil into a sandy slurry before you do it. But if you work hard, we can even keep eating chips together sustainably into the future. Thank you.